This lecture discusses about the Laplace transform. First, a transformation T is a mapping from one set A onto another set B. A typical example of a transformation is the differential operator D. From a set of function A to another set of function B, we have the transformation D. Example, for x squared, the derivative of x squared is 2x. So x squared is mapped to 2x under the differential operator D, or the transformation D. Similarly, if you have sine x, the derivative of sine x is cosine of x. If you have a constant 4, then it is mapped to 0. This is an example of a transformation. Another example of a transformation is a mapping from a set of triples or set of vectors R cubed to the set of real numbers. So the transformation is defined by T of any vector with components A, B, C equal to A plus B plus C. So for example, the transformation of the vector 1, 3, and -2 will be equal to 1 plus 3 plus -2, which is equal to 2. So from the set of R cubed to another set of real numbers R1, the transformation is T, and it maps the vector 1, 3, -2 to a real number 2. Another is, say, 1, 1, and 1. It is mapped to the real number 1 plus 1 plus 1, which is equal to 3. Now, these two types of transformations are also called linear transformations. T is a linear transformation if the transformation of the sum of multiples, say R of, for example, A plus S of B is equal to R transformation of A plus S transformation of B. If this condition is satisfied for any transformation T, then that transformation is called a linear transformation. The Laplace transforms fall under the so-called integral transforms. Okay, so an integral transform of a function, say f of t, is defined to be the integral from -infinity to infinity of k s t f of t dt, where k is called the kernel of the transformation. Okay, the transformation I. And an example of this integral transform is the so-called Laplace transforms. So, for any function f of t, for the function f of t, the Laplace transform of f of t denoted by L of f of t is defined as Laplace transform of f of t equal to the integral of e to the negative st f of t dt from 0 to infinity. In this case, e to the negative st is the kernel of the transformation. And the notation for the Laplace transform of f of t is the capital letter F of s. So from here on, we represent the Laplace transform of f of t by f of s. So from a function f of t, the transformation is to f of s. Okay, from f of t to f of s. And this is the defining equation of the transformation. So let us determine the Laplace transform of some elementary functions. First, we take the Laplace transform of a constant k. So k is a constant. So for the Laplace transform of k, we take on the definition that will be e to the negative st f of t dt from 0 to infinity. And since your f of t is equal to k, so this is your f of t equal to k, we have e to the negative st times k dt from 0 to infinity. Since k is a constant, we can write the integral as k times the integral of e to the negative st dt from 0 to infinity. Integrating e to the negative st dt, we have negative 1 over s. S is considered as a constant. We are integrating the variable t. So the integral of e to the negative st dt is negative 1 over s. S is treated as a constant from 0 to infinity. If we are to be strict about this should have been written as k times the limit of negative 1 over s. By the way, sorry, there is a missing term in the integral. It should be negative 1 over s e to the negative st from 0 to infinity. If we are to be strict about this, it should have been written as k negative 1 over s times the limit of e to the negative st from 0 to a, where a approaches positive infinity. Because this is an improper integral. Now, whenever you have an infinite limit, such as this one, it is called an improper integral. So the right way of writing the integral is to integrate e to the negative st dt and replacing the upper limit by some variable a and let a increase without bound. Okay, but from here on, we will drop the limit symbol, no? And we can just write the limit as 0 and positive infinity. So continuing, we have negative k over s, then e to the negative st from 0 to infinity. Negative k over s, e to the negative st is actually 1 over e to the st, okay, from 0 to infinity. Now, replacing t by infinity, the denominator will approach positive infinity. So it will approach positive infinity. E to the infinity is infinity. And 1 over infinity, no, the quotient of 1 divided by a very huge number, the limit will be 0. Okay, so it will be 0 minus the lower limit, substitute 0 to t, it becomes 1 over e raised to 0 or 1 over 1 equal to 1. So finally, negative k over s times negative 1 is k over s. Of course, s is greater than 0. So we write the Laplace transform of the constant k as equal to k all over s. So for example, if you want to find the Laplace transform of the constant 5, the answer is simply 5 over s. So the Laplace transform of pi is just pi all over s. Next, we take on the Laplace transform of e to the negative at. So here our f of t is e to the at. So the Laplace transform of f of t again by the definition is e to the negative st f of t dt from 0 to infinity. So the Laplace transform of e raised to at is equal to the integral of e to the negative st e to the at dt from 0 to infinity. We can combine e to the negative st and e to the at as e raised to negative s minus a of t dt from 0 to infinity. Since we are integrating with respect to t, negative s minus a is a constant. No? So when you integrate, it becomes negative 1 over s minus a e raised to negative quantity s minus at from 0 to infinity. So negative 1 over s minus a times, again, for the upper limit infinity, e raised to negative quantity s minus at is the same as 1 over e raised to s minus at. But since t approaches infinity, the entire denominator also approaches infinity, and 1 over infinity, the limit will be 0. So that will be 0 for the upper limit minus the lower limit is 0. Replace t by 0. Everything in the exponent of e will be 0, so e to the 0 will be equal to 1. So negative 1 over s minus a times negative 1 gives us 1 over s minus a. So the Laplace transform of e to the at is equal to 1 over s minus a. So let's have some examples. So what is the Laplace transform of e to the negative 3t? That will be equal to 1 over s minus negative 3. No? Our a here is negative 3. So 1 over s minus a or 1 over s minus negative 3, that gives us 1 over s plus 3. Another example, the Laplace transform of e raised to t all over 4. So that will be equal to 1 over s minus 1/4. Or we can write this as 4s minus 1 all over 4, which will eventually go up in the denominator. Okay? So, remember that the Laplace transform of e to the at is 1 over s minus a. Next, the Laplace transform of t. So our f of t is equal to t. Again, the Laplace transform of f of t by definition is e to the negative st f of t dt 0 to infinity. We replace f of t by t and we integrate t e to the negative st dt. So to integrate this, we will be using integration by parts. Na? Okay, so using integration by parts. We have u equal to t, dB is e to the negative st dt, so du is dt, and b is the integral of e to the negative st dt, negative 1 over s e to the negative st. Okay, so the integral of u dB is ub t times negative 1 over s e to the negative st. Okay, minus the integral of negative. So it becomes 1 over s integral of e to the negative st dt from 0 to infinity. This one 0 to infinity. Okay, so that will be negative 1 over s t e to the negative st from 0 to infinity. And the integral of e to the negative st is negative 1 over s multiplied by 1 over s is negative 1 over s squared e to the negative st from 0 to infinity. Okay. There is a term e to the negative st and the upper limit is infinity, so it will be 0. Minus the lower limit is negative, so positive 1 over s times t e to the negative st, and replace t by 0. So since one of the factors is 0, everything else will be 0. So that means that this approaches or will be equal to 0. Next, we have negative 1 over s squared. And e to the negative st, the limit of e to the negative st as t approaches infinity will be 0, minus the lower limit, replace t by 0, e to the 0 is 1. So the answer here is negative 1 over s squared times negative 1, or just 1 over s squared. So the Laplace transform of t is 1 over s squared. Now, similarly, the Laplace transform of t squared will be equal to 2 all over s cubed. So for the Laplace transform of t squared, you perform integration by parts twice. And the Laplace transform, you will get the Laplace transform of t squared, which is equal to 2 over s cubed. Generally, the Laplace transform of t raised to some power n is equal to n factorial all over s raised to n plus 1. So let us encircle this. So for any n, the Laplace transform of t to the n is an integer, it will be n factorial all over s raised to n plus 1. Even if n is 0, t to the 0 is 1. So it will be 0 factorial over s 0 plus 1. That will give you 1 over s. And that is exactly the Laplace transform of the constant 1. Okay? So n here refers to any integer, a positive integral exponent. Okay? How about the Laplace transform of sine kt? So f of t is equal to sine kt, where k is a constant. K is a constant. So the Laplace transform of sine kt will be equal to the integral of e to the negative st sine kt dt from 0 to infinity. Okay. We will again use integration by parts. So we use integration by parts. So what will be my u? What will be my u? My u is e to the negative st and dv is sine kt dt. So du is negative s e to the negative st dt. Remember, we are differentiating with respect to t, so negative s is treated as a constant. So the differential of e to the negative st is negative s e to the negative st dt. And v, we integrate sine kt dt, k is a constant, that will be negative 1 over k cosine of kt. So, the integral of e to the negative st sine kt dt from 0 to infinity will be u times v. That will be negative 1 over k e to the negative st cosine of kt minus the integral of the product with du. So negative times negative is positive k over s. That will be negative k over s e to the negative st dt, e to the negative st cosine kt dt 0 to infinity. And this part is also evaluated from 0 to infinity. Okay? So, that will be negative 1 over k. Let us substitute later after we have evaluated the integral. No? So there will only be one substitution. So negative 1 over k e to the negative st cosine kt minus ks integral of e to the negative st cosine kt. So in this case, we will apply again integration by parts. So we will apply again integration by parts. Our u is e to the negative st, dv is cosine kt dt. So du once again is negative s e to the negative st dt, and your b is 1 over k sine of kt. So negative ks, we continue, negative ks times uv 1 over k, 1 over k, sorry, what do we have here? It should be, I think there's something wrong. This one, it should be negative s over k. So that should be negative s over k there, right? So I have to change this also into negative s over k. Alright, so ub is e to the negative 1 over k e to the negative st sine of kt minus the integral of b du. There is a negative there, so it becomes positive. and that is s over k e to the negative st sine kt dt from 0 to infinity. Okay? So let me write this as negative 1 over k e to the negative st cosine kt minus s over k squared e to the negative st sine kt, and then minus s squared over k squared integral of e to the negative st sine kt dt. Alright? From 0 to infinity. Now these two will also be evaluated from 0 to infinity. 0 to infinity, 0 to infinity. But you see that there is a recurrence of the integral e to the negative st sine kt dt. That is this one. So what we do is we transpose this to the other side. At the left side, it is e to the negative st sine kt dt. The coefficient actually is 1. So we have to add this coefficient. It will become 1 plus, we just add the 2. It becomes 1 plus s squared over k squared integral of e to the negative st sine kt dt from 0 to infinity. Alright? And that will be equal to negative 1 over k e to the negative st cosine kt minus s over k squared e to the negative st sine kt from 0 to infinity. Alright, so 1 plus s squared over k squared gives us s squared plus k squared all over k squared integral of e to the negative st sine kt dt from 0 to infinity. So we evaluate the left side, the right side by substituting the upper limit infinity to t. So since we have e to the negative st, that will approach 0. Here, e to the negative st also, that will be 0. So as for the upper limit, this entire thing will be 0. Minus the lower limit. Okay? The lower limit, negative 1 over k, e to the 0 is 1, and cosine of kt is also 1. So e to the negative st cosine kt will be equal to 1 minus s over k squared. E to the 0 is 1, but sine of 0 is 0. So that will be 0. So what we have is positive 1 over k. Alright, so 1 over k. So this will be s squared plus k squared over k squared e to the negative st sine kt dt from 0 to infinity. We can cancel the k here. We can cancel k and 1k. Alright, so finally, the integral of e to the negative st sine kt dt from 0 to infinity will be equal to k all over s squared plus k squared. So the Laplace transform, we write the Laplace transform of sine kt as k all over s squared plus k squared. There. So as an example, the Laplace transform of sine 4t is equal to, our k here is 4, so 4 over s squared plus 4 squared, or 4 over s squared plus 16. Alright? Now, the next one is the Laplace transform of cosine kt. Following the derivation of the formula for the Laplace transform of sine kt, the Laplace transform of cosine kt will be equal to s over s squared plus k squared. Take note, the numerator now is s instead of k. So for sine kt, it will be k over s squared plus k squared. But for cosine kt, it will be s all over s squared plus k squared. So, example, the Laplace transform of cosine 3t will be equal to s all over s squared plus 3 squared, or s all over s squared plus 9. Okay? You can also derive the Laplace transform of hyperbolic sine of kt, which is equal to k over s squared minus k squared. And the Laplace transform of hyperbolic cosine kt will be equal to s over s squared minus k squared. Alright? Now, supposing that we are given f of t as a piecewise function equal to 4 if t is from 0 to 2, and t if t is greater than 2. Okay? Find the Laplace transform of f of t. So the domain from 0 to positive infinity is divided into two intervals, t from 0 to 2 and t greater than 2. Let us just use here the strict inequality. Okay. So the Laplace transform of f of t is equal to the integral of e to the negative st f of t dt from 0 to infinity. We will divide this, we will rewrite the integral as the sum of the integral of e to the negative st times f of t, which is 4 dt from 0 to 2, for the interval 0 to 2, plus the integral of e to the negative st times f of t, which is t from 2 to positive infinity. Okay, since f is a piecewise function, we shall write the integral as the sum of two integrals 0 to 2 and 2 to positive infinity. So the integral of 4 e to the negative st is negative 1 over s e to the negative st from 0 to 2, plus for the integral of e to the negative st times t dt, we shall apply here integration by parts, where u is equal to t, db is equal to e to the negative st dt. So du is dt, and b is negative 1 over s e to the negative st. So for the integral of e to the negative st times t dt, it will be ub negative 1 over s t e to the negative st minus negative, so that will be positive 1 over s integral of e to the negative st dt from 2 to infinity. Okay? So, we have here negative 4 over s e to the negative s times 2 or negative 2s minus e to the negative s times 0, that will be 1. Now, we substitute the upper and the lower limits. Then, minus 1 over s t e to the negative st. The integral of e to the negative st is negative 1 over s times 1 over s. That will be negative 1 over s squared e to the negative st from 2 to infinity. Alright. So what we have here is, I can write this as positive 4 over s, 1 minus e to the negative 2s. And this one, negative 1 over s, okay? Substituting the upper limit of infinity to e to the negative st, that will be 0. Okay? Then minus 1 over s squared e to the negative st, that will also approach 0. So that will be, everything there will be 0. Okay? Then lower limit 2. Negative 1 over s, t is 2. So times 2 e to the negative 2s. So, by the way, it is negative, negative, no? Because we are using the lower limit. So negative, negative, that will be positive. And this one, negative, negative, or minus negative 1 over s squared e to the negative s times 2 or negative 2s. Alright? For the upper limit infinity, both terms, these terms will be 0. Okay? That is for the upper limit. Then we subtract. So negative and negative, that will be positive. Oh, the same thing here, it should also be positive. No? Minus negative. So that will be positive. 1 over s squared e to the negative 2s. So, what do we have? 4 over s minus 4 e to the negative 2s over s plus 2 e to the negative 2s over s plus 1 over s squared e to the negative 2s. We can simplify this. Negative 4 and 2 is negative 2 e to the negative 2s all over s plus e to the negative 2s over s squared. Alright? Now we can combine them. 1 over s squared times 4s minus 2s e to the minus 2s plus e to the minus 2s. Okay, so that is our final answer.